objective is that we can determine patterns that identify an exponential function from its related common ratios. And your warm-up before you turned it in was to write a complete sentence, writing your own situation that is exponential. For example, like the notes you have in front of you, bouncing ball, okay, whether it be a basketball or a soccer ball, is an exponential situation. So, let's take a look at these 1.5 notes. Oh well, hopefully this doesn't die. So, Deanna dropped a basketball and let it bounce several times. What would a graph of the height of the basket versus time look like? Okay, so what do you think if I have height over time? What do you think it would look like on a graph when I drop a ball? What do you think it would look like? Any ideas? Okay, it would bounce back up. So now, would it drop straight down, or would it be kind of gradual? What do you think? Okay, if you know a little bit about physics, gravity is accelerating, so it gets more steep like that, and then it's going to bounce up. How far up do you think it's going to go? A third of the way, maybe? Okay, whatever. So you get it. It's bouncing, right? We'll see what it turns out to be when we look at the example. But on this Explorer part, it says, according to international basketball guidelines, basketball should be inflated such that when dropped from a height of 1.8 meters, the ball should bounce and rebound to a height of at least 1.2 meters, but no more than 1.4 meters. So basketballs, obviously they got to bounce to dribble, but they're not supposed to bounce too much or too little, right? If they bounce too much, it's like Space Jam, it's going everywhere. But if it's too little, you can't dribble it, it's not enough. So that's how you know you got a good basketball, based on how much it bounces. And bounce height is an important aspect to making sure that a ball used in any sport is properly inflated and not worn out. Looking at you, Tom Brady. Well, anyways, this Explore activity, I wasn't able to get a hold of these materials. So instead, I have this little video to show you that will simulate it. It is a soccer ball instead of a basketball, but it's all right. So let's restart this over here. All right, so this guy drops a soccer ball. Let's see if I can make it bigger. So that looks like a little more than 1/3 of the way, but that's all right. Now, the colors aren't that awesome, so I don't know if you can really see those numbers, but it's going to clear up right there. And you can see this going down. Mrs. Marrero, what did you say that fancy word for this again is? When it looks like it's going down like this? Like this? Exponential what? Decay. Okay? And I'm not talking about like, Smash Bros. DK, like Donkey Kong. No, I'm talking about D-E-C-A-Y. Going down. Kind of like tooth decay. Your tooth goes down when you don't brush your teeth. Brush your teeth, everyone. So, what? Tooth decay? It's a real... Yeah, they rot. They rot out, So, drinking too many sodas, not flossing, then your breath stinks and everything. So anyways, that decay is always bad, I guess. But sometimes decay is good, like, it'd be good to decay. What? What's good to go down? What? Leaves, so you don't have to rake them. So, decay is going down, and growth would be going the other direction, going up. So you got exponential decay, you got exponential growth, right? Now, all these numbers, we're going to try to remember here in a second as we fill out our table. So when we flip this over to the next page, okay? So everyone's with me? Everyone? Next page? Now, we're going to modify this because we're not actually measuring these on our own, okay? I want you to make another little column over here for bounce. We're modifying this thing. Bounce number, okay? So I want to know, before I let it go at the 0 bounce, how tall was it? And then 1, 2, 3, 4, 5. Okay? And we're going to scratch these 3 out. And I'm going to cross out the title of this one, okay? So y'all can modify this with me. Cool. Okay. So I'm going to use the information from that video we just watched. If I can move something here. No. No. Why does this always happen? There we go. Boom. Okay, now back to the video. Now you can kind of barely see it, but this first one was 215. Let's write that down. Oops. Okay, so 215. And then we have 136 after the first bounce. Bounce 1, 136 centimeters. Second bounce, 96 centimeters. Third bounce, 71 centimeters. Fourth bounce, 55. Fifth bounce, 45. Okay. Now, you can see it in the video itself. Okay. When we were thinking about graphing it on the front side, this was kind of what we were looking at, and that's right. Okay. What are these little hills called? What's the math word for that? Starts with a Q. You remember that stuff? Well, the type of function starts with a Q. Quadratic. Quadratic. But it makes a P parabola. You remember parabolas? Parabola. So, yeah, so you got quadratic equation. That makes a parabola. A bunch of little parabolas there. Cool. All right, all that to say, we are down here. Now it tells us to do 2 things on number 2 and 3. First, we're going to calculate the finite differences, and then we're going to calculate the finite, or sorry, the blah 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 average bounce, the ratios. Okay. So first, let's do the differences, and then we'll do the ratios. So I'll do this on a calculator in my hand here. It won't be on the screen. But we're doing 250. Remember, difference means subtraction, right? So we're doing okay. So 136 minus 215 is negative 79. Okay. Now I want y'all to notice I'm subtracting bounce 1 from bounce 0, so that way it is negative because it is going down, right? Okay, 96 minus 136, negative 40. Okay, 71 minus 96, negative 25. Okay, 55 minus 71, minus 16. 45 minus 55 is negative 10. Now, obviously they're not all the same, but the question is, are they about kind of staying in the same ballpark? And I would say no. From 79, that's close to 80, down to 40, that's halfway, and then down to 25, that's decreasing at such a big amount, okay, that I could not call that linear. And again, when we look at this picture, this is not linear because it has to curve down, right? So you can kind of see why it's not linear. Cool? So the differences, we calculated them in blue up here, okay? Do they appear to be linear? No. The differences are too different. Okay? Again, when you work with data, all data rarely is something specifically exactly on the money. But in this case, it's too different. Cool. Now, next one, we're going to do the common ratios. Let's do that in purple here. Now, when we do ratios, you're dividing this time, okay? So I'm going to divide 136 divided by 215. So let's find these ratios. I left my calculator. Okay, so again, we're dividing these numbers. 136 over 215. And we get, now, whenever you do these, let's see here. No. Oh well. Whenever you divide, you want to hit Control Enter so you can get the decimal. So the decimal I got when I divided was 0.63. Okay? Now I'm doing 96 divided by 136. Control Enter. 0.71. 71 over 96. Control Enter. 0.74. 55 divided by 71, Control Enter, 0.77, and then 45 divided by 55, 0.82. Now, I know this is increasing each time, but for the most part, it's pretty close together, okay? It's about, you can see it's a little bit below and a little bit above 0.75, and that's kind of about where we're going to be doing when we do our regression, right? So we got our common ratios written out. Now the question is, for number 4, what is the starting point or the y-intercept of the data? Now, there we go. What is the y-intercept in this table? Y-intercept is when x is what? What? Yes. I think Miss Moreau needs to sing to y'all because y'all are half awake. We don't know what the y-intercept is.
When x is 0, what is y? The y-intercept.
And on that farm... Oh. All right. It's okay. So the x, when the x is 0, that's the y-intercept. So the x bounce is 0. That's where we started to drop it, right? So the y-intercept is 215 centimeters. That's where we started in the video bounce drop, okay? Now, we're going to take that information and we're going to use our calculator to get a exponential function. So I'm going to freeze that over there. And again, we know how to use regressions. Let's use regressions, right? So we go to lists and spreadsheets, x at the top, y at the top. And we're going to put in just 3 of these, okay? So 0, 1, 2. And then we got 215, 136, 96, okay? Usually we only put in 3, but I'm going to put in all this data. Let's do it right here. Do it all. 1, 2, 3, 4, 5, and then we got 96, 71, 55, and 45. Okay? So again, menu 41A for exponential, x is x, not q, x is x, y is y. All right. Now, my r squared is not exactly 1 because, again, the common ratios are not exactly the same, but it's close to 1. So I get an a value of 192.77, okay? So let's do that. Let's write this down. Y equals my a value. I'm going to freeze it. Okay, my a value was 192.77, okay? Times b, so parentheses, the b value I got from the calculator was 0.73, okay? And again, about 3/4. And then to the power of x, okay? So again, we put in all the information. We use the exponential regression. We get the equation, okay? Now we just got a few more questions to answer. What do the y-intercept and the rate of change mean, okay? Back to number 5 again. We didn't do differences. We found a common ratio, okay? And again, it was not linear, but it was exponential. But when we're finding those rate of changes, okay, each time, and then we use the regression to get the rate of change, okay, that's my b value that I put in parentheses. So let's start with y-intercept. The y-intercept is always this first number, 192.77. Now again, from our data, before we did the regression, we started at 215. So the regression is the best fit to this data, okay? So again, 192.77 is from the data, from the regression. It is the starting amount where it was dropped. Okay? So again, in the original data, we dropped it at 215. When we do the regression, okay, it has to adapt to the data. Next thing we have here is the base. The base is in the parentheses, okay? And that is our multiplier. That's how much it's changing each time. The changing amount, or the changing value, okay? Now, using this model, we want to predict the height of the 8th bounce. So again, if we have an equation, how have we done this in the past? How do I go from an equation to a certain term? What's one way I can do it? How do I get a table list that I can look at? I graph it, and then I hit Control T, right? Another way I can do it is to replace this x with 8. So there's 2 ways to do it. If you want to just type it in to the calculator part with an 8, that's fine. If you want to graph it and look at the table, that's fine too, okay? Let's do the graphing way. So I'm going to go to a new document, add graph. My graph was 192.77 times 0.73 to the power of x. I hit enter. Can't really see the graph. That's fine. I hit Control T because I need the table. And I'm looking for the 8th term, which is 15.55. We're going to round that. Okay? So 15.55. How did I get that? Graph, Control T. Now we're going to skip 8 and 9. Okay? We don't have a basketball to measure circumference and diameter. Okay? So the gist of this today is that you can take data, you can find the common ratios. Again, you can still get the equation even for exponential decay. Tell me what the y-intercept is, tell me what the base is, tell me a certain value. A lot of the stuff we've been doing, and again, for exponential. Okay? So we'll have an assignment on this tomorrow. And by that I mean Monday. All right.